Okay, so hi everyone. We'll discuss the Jan 22 Mechanics Paper 3. Okay, so we'll start with question number 1. They say a uniform lamina is in the shape of the region R. Region R is bounded by the curve with the equation y equal x times x plus a, where a is a positive constant. The positive x-axis and the line with the equation x equal a. Okay, so the region R is bounded by this curve and it's bounded by the positive x-axis and it's bounded by the line x equal a as shown in the shaded figure 1. Find the y coordinate of the center of mass of the lamina. Okay, so you're supposed to find the center of mass. Now you can see clearly this is a 2D object, right? So basically you need to work with, you need to find the center of mass of this 2D lamina. Okay, so how do you start working on this? So what's the idea? So guys, these are the formulas that are available. So you need to know these, right? So for a uniform lamina bounded by the x-axis and the curve. Okay, so this is what I think this is the very first formula you'll find in your center of mass lesson, right? In chapter 5. In chapter 5, so this is the very first equation they introduce you. Okay, so I think in the okay, so it's given as x bar equals the integral of xy with respect to x over integration of y dx, and y bar is equal to integral of half y square dx over integral of y dx. Now here, so what do they want us to find? They want us to find the y coordinate. So you really don't need to go for the x bar. You will need to find the y bar, right? So how do you find the y bar? So it's really easy. All you need to know is the existence of this equation. So this is already there in your textbook. It's been covered. Even these equations have been derived, right? So you also should know how to derive these equations if required. Okay. All right. So here you can directly use the equation. Okay. And then and because they're not asking you to derive anything, you can directly go with these equations. And then so let's apply. So integral of half y square dx. So dx means with respect to x over integral of y dx. So then dx means you need to input the x limit. So guys, you can see here this particular region R starts from the x value 0, ends at the x value a. That's why the integral limits are 0 to a, right, in both the cases. And then you need to input the value of y here. So the y function is given to you, right? The y function is x times x plus a. So all you have to do is input the y function as x times x plus a. So what I'm doing here is I'm going to take the numerator separately. So you can do, I think it's best to, kind of get the numerator denominator separately and then integrate. So you can see here I've replaced the y with x times x plus a, right? So y is x times x plus a, and then when you're squaring it, because it's y square, this becomes x square times x plus a square. Do you agree? Because you're squaring, right? X plus a, when you square, it's x square, x plus a square. Right, guys? And then you need to expand the bracket. So x square stays, and x plus a square is x square plus 2ax plus a square. Right, guys? And then, in order to integrate this, you still can't integrate while there's a product. We need to get inside this. So how do you get inside this? You can see I'm multiplying inside with x square. X to the power 4, 2ax cube, and x square a square. All right, so this is just still the expansion. We still did not integrate. Okay, so this is the expansion, and then finally, at this point, we are ready to integrate. Then we can integrate this x to the power 4 integration is x to the power 5 over 5. 2a is a constant, x cube integration is x to the power 4 over 4 plus a square, x square, a square is a constant, that stays, x square integration is x cube over 3. And you can put your limits from 0 to a because you're done with the integration. Now you can go with the integration limit. So they ask you to, so we have to give the answer in terms of a, right? Because we are not supposed to find a, the answer should definitely come in terms of a. Okay, and then you can input the limit. First x is a, and then the other limit x is 0. Right, guys? So this is a matter of simplification. 1 over 5 plus 2 over 4 plus 1 over 3, and you can add them, and you can get the y bar coordinate. So this is basically not the y bar coordinate. This is basically the numerator, right guys? Because you can see here I was working on the numerator of y bar. Okay, I was working on the numerator of y bar. So I also have to get the denominator of y bar, right guys? So also need to get the denominator of y bar. So integration of y dx. So the limit from 0 to a, and y is x times x plus a. And then you can directly expand the brackets x square plus ax, that's the expansion, and then you integrate. When you integrate, it's x cube over 3 plus a is a constant, x integration is x square over 2, right guys? And then you input the limit. So you get here a cube over 3 plus, yeah, I mean here the a square and a gives you a cube over 2, and then minus, when you input the x limits as 0, this guy is completely 0, right? And you can add this part, 1 over 3 a cube plus half a cube gives you 5 over 6 a cube. All right, and at the end of the day, you need to input the values for the numerator and denominator. So I got the numerator answer separately as 31 over 68 to the power 5. And I got the new denominator answer as 5 over 68 to the power 3. All right, and all I have to do is substitute these values into the equation. Okay, 31 over 68 to the power 5, 5 over 68 cube. And you can see I can get my answer for y bar. All right, so the final answer, the answer is 31 over 50 into a square. Okay, so that's the answer for y bar. Okay, guys, we'll move on to question number 2. So they say here a particle of mass m is attached to one end of a light inextensible string of length 12. Okay, the other end of the string is attached to a fixed point A above a smooth horizontal flow. The particle moves in a horizontal circle on the floor with the string taut. The center of the circle is the center O of the circle is vertically below A, with OA equal to L as shown in figure 2. The particle moves at constant angular speed omega and remains in contact with the flow. Show that omega is less than or equal root g over L. So guys, how do we do this? It's an 8-mark question. Okay, so first thing we need to realize is number one, that this is, we are working with circular motion here, right? This is the particle moves in a horizontal circle. Because when it comes to circular motion, we deal with specifically two types of circular motion, horizontal one, and there is another type called the vertical, right? So this is a horizontal circle. So you have this is the point where one end of the string is fixed. This is the other end, and at the other end this is the end where you have the particle, and this particle is going to rotate in a horizontal circle. Okay, so it's gonna move in a horizontal circle. That's what you have here. Okay, so this O is the center, and around O it's gonna move in a horizontal circle. Okay, guys, so you need to now show that this inequality holds. Okay, so what do you need to do here? So guys, when it comes to horizontal circles, there are only two things to do. That is, you need to consider the vertical equilibrium, because even though the particle moves in a horizontal circle, it is vertically in equilibrium. All right, and then the second thing to do is to apply F equal ma towards the center, right? Those are the two concepts, and you should be able to derive any answer that they give you by using those two concepts. Okay. All right, so let's get started. So you can see the first thing I've done. The first thing I've done here is since they've given me two lengths of the right angle triangle here, right? So you can see here, this is kind of like, if I consider this as a right angle triangle, I've got the hypotenuse length and I've got the opposite length here, and I can actually derive this angle, right? So I've derived it as 30. So how did I get that? You can see I've used sine theta. So I've taken this angle as theta first. So sine theta opposite over hypotenuse, that's L over 2L, and I get half, which gives me the theta angle as 30. So this is knowing the angle is a big advantage. Okay, because now that's one unknown that you got, that you don't have an angle as an unknown anymore. That's really important. Okay, so we found the angle. Okay, so now let's go for our two main concepts, considering vertical equilibrium and considering F equal ma towards the center. So guys, before we apply vertical equilibrium, you need to mark all the forces acting on the object, right? So guys, you can see here I've marked all the forces. So how did I get all of this? First thing is it's attached to an extensible string and it's going in a circular motion. So definitely you have the tension, right? So tension on the object, the tension acting on the string, right? And then the particle is on the flow. So if the particle is on the flow, guys, you can see there is a contact with the flow, which means you have a normal reaction, right? It's a normal reaction. And then you definitely have the weight of the object acting vertically downward. So there's no frictional force or whatsoever because it's on a smooth horizontal flow. Okay, so these are the only forces. Do you agree? Normal reaction, the tension, and the weight. Okay, so then that's all we require, right? That's all we need. So now we can go for vertical equilibrium. So how does it work? So you can see here, normal reaction is acting upwards. That's what I've written here. And this tension, you can resolve, right? So the tension can be resolved, and you get here away from the angle, you get T sine 30, right? And then you should get T cos 30 to the other side, to the horizontal side. So I need the vertical one, so T sine 30 and this R are acting vertically upwards, and that's equal to mg. Okay, so that's one equation. And then, guys, the next one, we apply F equal ma towards center. So towards center. So when you apply this towards the center, what are the forces acting towards the center of the circle? Now, guys, first thing is you should identify the center of the circle is at O, right? The center of the circle is at O, not at A, right? The horizontal circle is around O. So the horizontal component is T cos 30. Okay, equals mr omega square. So this is the equal ma equation, right? So the centripetal force is T cos 30. Okay, now none of the other forces are having giving any components towards the center, right? R and mg are perpendicular, the horizontal, so they don't give any components. So T cos 30 is the only component towards the center. So that's equal to MA, the mass, and acceleration is, you can use R omega square or V square over R. So I'll go with R omega square because we're trying to derive something for omega, right? So that's why I chose R omega square. But you also have centripetal acceleration as V square over R. So, I mean, use the formula that is best working for the situation. So in this situation, since I want omega, I went with R omega square. Okay, so let's substitute the values. So T cos 30 equals mass is M, right? The mass is M here, mass M. And the radius. So guys, the radius of the circular motion is this OP distance, right? Because the particle is revolving around O, the radius is this. And you can see we can actually get the radius, right? How can I get the radius? Because I can resolve the hypotenuse 2L and write as 2L cos 30. Can you see? This 2L cos 30 that I've written here is the radius. Okay, that's resolving the hypotenuse of the right angle triangle, the length. So 2L cos 30 into omega square, and then the cos 30 can be removed, and you get T equals 2L m omega square, right? So that's the tension, and then okay, and then guys, you can see I'm going to input the tension value back to the first equation, the vertical equilibrium equation. So R plus T sine 30 is equal to mg, and you replace the T value with 2L m omega square, right? So let's replace the tension here with what you found. So when you replace the tension value with 2L m omega square, you get R plus, so this 2L m omega square sine 30 is equal to mg, right? So you can see what am I trying to do here now? Nothing is okay. We can substitute all of these into the equation, but what's our final goal? Why am I going through all of this? You can see now in order to get this inequality, like, okay, so how do I build the foundation for this inequality? Okay, how do we build the foundation for the inequality? So you can see here the way I'm going through this is actually I'm going to use this all these stuff that we placed to actually derive equation, or I'm trying to derive some kind of a value for R, the normal reaction, right? So here the normal reaction, I get here mg minus 2L m omega square sine 30. Sine 30 is half, half and 2 can cancel here, and you get mg minus L m omega square. So why did I go through this path, and why did I go find R? Okay, guys, because whenever you are trying to derive some sort of an inequality, especially in these kinds of circular motion questions, okay, you need to set some one of your forces to maybe probably greater than or equal 0, right? So for example, over here, so what I'm going to do here is I'm just going to make a claim here. Okay. And then work on trying to get the inequality. So for example, here you can see that R is the normal reaction, right? And the circular motion is going to work as long as what? As long as the particle, this circular motion is going to happen as long as the particle is in contact with the ground, right? Because if the maybe if the speed increases, the particle can, it can go above the ground, right? If the speed increases, but in order to maintain, okay, in order to and remains, I think they say here, right? The particle moves with constant angular speed and remains in contact with the flow. Okay, so the particle also needs to remain in contact with the flow, right? Because so in order to have that condition, okay, to make sure it's remaining in contact with the flow, you need to set your normal reaction to greater than or equal 0. Because the normal reaction greater than or equal 0 means you are in contact with the ground. Okay, so you're not leaving. Okay, so greater than or equal. Okay, so it can be greater than or equal. So just this is the condition that you need to set, and immediately you can see you can now get your answer, right? So it's just a matter of substituting the R value and then taking the Lm omega square, removing M. M is a positive constant, so you can remove it without having any issue to the inequality. And then you get here G over L omega square. So omega is less than or equal root G over L as required. Okay, guys, so this is the answer. Okay, guys, so we'll move on to question number 3. A particle P of mass m kilogram is initially, so at time 0, that is, held at rest, which means at time 0, velocity is 0. At the point O, so normally point O you can consider as your displacement 0 position, okay, on a smooth inclined plane. It's a smooth inclined plane. The plane is inclined at an angle alpha to the horizontal where sine alpha is 2 over 5. So when they give you sine alpha is 2 over 5, you can immediately get the value of cos alpha, sine alpha, and you can the value of cos alpha, right? Because most of the time when you're working with, when you're resolving, you'll need sine alpha and the cos alpha. So you can quickly derive the value of cos alpha, right? I think that's pretty standard. Okay, so then the next part, the particle is released from rest and slides down the plane against a force which acts toward O. The force has magnitude 1 over 3 mx square newtons, where x meters is the distance of P from O. Find the speed of P when x equals to 2, so it's 6 miles. Okay, so first thing is to kind of like visually have an idea of what's going on, right? So what's going on here? You need to kind of have a visual idea. So what do they say? Again, they say so the particle is held at the point O, right? The particle is held at the point O. So this is the place where the particle is at time 0. At time 0, it's at rest and it's at the point O. The particle, then they say the particle is released from rest, right? So that's what you're having, what's happening here, and slides down the plane. Can you see? So this particle is going to go down the plane against a force which acts towards O. So that's I think you can see here. So when the particle is on its way down, there is a force that's acting against, and that's what I have marked here as F. Right, guys? Can you see? So this Fv is what I have marked here as 1 over 3 mx square, the resistive force. Okay, so that's what I have marked here as F. Do you agree? Okay, and then, you can make your own diagram, right? So this is just my diagram where I've marked the F towards O, right? The particle is on its way down, F is acting against. That's what they've said here. So you're supposed to find the speed. Okay, so before finding the speed, of course, you need to first mark the complete force diagram. So you can see what I've done. I've marked all the forces here. So you have your weight acting vertically down. You have the normal reaction right here. You have the normal reaction acting perpendicular to the plane. Okay, and then mg. Then I've resolved the weight. Okay, so mg cos alpha acting perpendicular to the plane and mg sin alpha acting along the plane, right guys? So this is basic M1 stuff. Okay, so these are basic M1 stuff, mg cos alpha away from, perpendicular to the plane, and mg sin alpha, right? So because I want to work with forces parallel and perpendicular to the plane. Okay, so now let's work with, let's try to find the speed. Okay, so how do we find the speed? So guys, you can see here, first of all, the first thing you need to notice here is that the force, the resistive force they've given you here is a function of displacement. So this is actually, you should, when you see this question, you need to remind yourself this is a question from chapter 1, right? Because in chapter 1, you were dealing with forces that were functions of time and forces that were functions of displacement. So here forces, the force is a function of displacement. Okay, so then you need to recall that we used different equations for acceleration in each situation. If the force is a function of time, we used the acceleration as dv by dt. But if it is a function of displacement, you use acceleration as v dv by dx. I think there was another expression in the book as well. So you can go with anyone, right? So you can see what I've done here. So I'm going to use F equal ma because I need to involve acceleration. Okay, F equal ma down the plane because the particle is on its way down along the plane. So along the plane, what are the forces it needs? It has mg sine alpha acting down the plane. Resistive force is F. Okay, mg sine alpha minus x equals m. A acceleration is v dv by dx. All right, acceleration is v dv by dx. So this is important because the reason I've gone for this is because the equation, because this equation, when I input the f value, it's gonna be a function of displacement. That's the reason we go for v dv by dx. Okay, so here these are the two equations you've learned. So I've gone for the appropriate one here. Okay. And then guys, so you can see what I've done here. I've replaced the f value with 1 over 3 mx square. And I've cut off the m is common to everyone. And you can see what I've done here, right? So I've kind of like done a variable separation from something you do in P4, right? So here v and dv and the dx here because the entire thing is gonna be considered with respect to x, right? So I took the dx here and then you're gonna integrate both sides, right? Because I want to find v and I need to get rid of these dx's and dv's. So we integrate the whole thing because anyway, from acceleration, if you want to go to velocity, you'll have to perform an integration somewhere down the line, right? So here I did the variable separation and then we integrate. So here the integration happens on the left side with respect to x. On the right side, the integration happens with respect to v, dv, right? So it's happening with respect to v. So here g sine alpha is a constant, right? Because yeah, integration is happening with respect to x and there's no x term here. So g sine alpha is just a constant, and when you integrate a constant, you just get x. So that's why you get here x g sine alpha. Minus 1 over 3, here there is x, so when you integrate, it's going to be x cube over 3. Equals just v integration with respect to v is v square over 2, right? And then in this case, because there are no integration limits, you need to input the plus c. Okay, because there are no integration limits, you need to input the plus c and make sure you find this plus c by substituting the initial conditions because they've given us at time 0, velocity is 0, x is 0. So you can substitute all of those values at time 0. Yeah, so velocity v value is 0 when x is 0. So you can substitute that. I think you can see when x is 0, you can see here this is, the first term is 0. And here also when x is 0, the second term is 0 equals here when v is 0, this term is also a 0, right? So you get c equals to 0 because when v and x are 0, your c is going to be 0. So we need to find that. You can see I found that. And after I find it, I'm going to substitute that back into this main equation and I rewrite it, right? So I get here, I think I've just written the same thing, but I've just written v square over 2 in front because I'm trying to find the velocity equals xg sine alpha minus 1 over 9 x cubed, right? The same guy, just replacing c with 0. And then I made v square the subject, that's taking 2 to the other side, 2x g sine alpha minus 2 over 9 x cubed, right? And then what have they asked us to find? Find the speed of p when x is 2, right? So I got the expression for v square and all I have to do is replace x with 2. Replace x with 2 and we replace g with 9.8, right? So whenever g is required, you input g as 9.8. And you can get your answer and make sure you give it to 3SF or 2SF whenever you use the G value as 9.8. Make sure that you do not exceed the significance, right? So I think you know this from M1 and M2. Okay, so either 3SF or 2SF, if you give the G value, you should not keep an exact answer. Okay, when you use 9.8. I think this is something that you're familiar. All right, so that's the answer for B. And then moving on to part B. 2 marks, the particle first comes to instantaneous rest at the point A, find the distance OA. So when the particle comes to instantaneous rest, guys, so you know what you should do here, right? And it's just 2 marks, so it should be pretty obvious. What do? I set the velocity to 0, right? Because if it's to come into rest, then it means the velocity should be 0 at some point. So we set it to 0. Okay. So the velocity comes to 0 because of probably the resistive guy, right? It's acting against. I think you can see the resistive force gets larger and larger as x gets as you have more distance from O. Okay, so that's what's happening. Okay, so let's get the answer here. Okay, and then so guys, I replaced the v with 0, and you can see so I'm going for a factorization method here, right? So I took 2x out and I had g sine alpha minus, if I take 2x out, it's going to be 1 over 9x square, right? So it's like a basic factorization. So either 2x is 0 or g sine alpha minus 1 over 9x square is 0. So I get here 2x is 0 means x is 0. So this is basically, this is true, right? Because your velocity was 0 when x equals 0. That was the initial condition, right? So we are setting our velocity to 0 and finding the places where x is equal to. At what x value our v equal to 0. So we get here 1x as 0. This is pretty obvious, right? Because that was what we used. We know that v0 is at x equals 0. And the other one, g sine alpha minus 1 over 9 x square is 0. So g sine alpha equals 1 over 9 x square. So you can see I've input the sine alpha value and you can get the x square, right? So you can input the g as 9.8 and you can get the, if you input the g as 9.8, you can give your answer here to 3SF or 2SF. And so this is the x value. So just 2 marks, right? So you really don't have to think much. Okay. Yeah, so basically, I think you guys were asking me about part A, like, so another alternative, right? So actually using the energy, yeah, the energy, worked energy principle, it's also possible to do part A, right? So you can try that. Okay, so I've just done it in the method I felt was the easiest. All right, so yeah. So moving back to part B, yeah. So you can give your answer here. If you keep your answer in terms of G, they've not told us explicitly keep the answer in terms of G. So here I've used G as 9.8, but if I use G as 9.8, I need to make sure I give my answer to SF or 3SF. So guys, here remember to square root as well, okay? Because it's x square. So to get x, you need to square root this answer and then either give it to 3SF or 2SF. Okay? So guys, we'll move on to question number 4. A thin, uniform, right, hollow cylinder, right? Okay, so there are some important words here. It's a thin, uniform, right, hollow cylinder, which means it's empty inside. Okay, so it's a hollow cylinder of radius 2a and height ka, has a base but no top. Okay, there's a base. The cylinder doesn't have a top. Okay, a thin, uniform, hemispherical shell. Can you see hemispherical shell means it's empty inside, okay, inside the hemisphere. Also of radius 2a is made of the same material as the cylinder. The hemispherical shell is attached to the end of the cylinder forming a container C. The hemispherical shell is what you have attached on top here. The open circular rim of the cylinder coincides with the rim of the hemispherical shell. The center of the base of C is O as shown in figure 3. Okay. Okay, so this is the base and you're supposed to, okay, show that the distance from O to the center of mass of C. C means the entire thing, right? Okay, the distance, okay, they want you to find the distance from O to the center of mass of C is this particular expression. And you can see you got 5 marks for this. Okay, guys. Okay, so how do we build the concept here? How do we find the center of mass of container P? Okay, first thing you notice here is that it is symmetric, which means you can say that you only need to find one coordinate, right? Because if you consider this as like the y-axis and you measure from O, you can see that you are x by 0. Can you see? You only need to find the y coordinate, like the y distance above O. Okay, you only have to find one coordinate, right? The other coordinate is that's what they say here. Show the distance from O to the center of mass. So from O to the center of mass distance is what you need to find. Okay, so now what's the concept here? Okay, so what's the concept to find the center of mass, right? So normally, I think you guys should be familiar. So in the theory classes, we've gone through these kinds of questions, right? So I think so. This is the method that we go with, right? So we actually break this large object into objects that we can work with, right? Into more smaller and simpler objects, right? So guys, I'm going to break this into object mass and center of mass. And the first object I'm going to consider is the hemisphere, the hemispherical shell. Okay, and we are going to write the mass and the center of mass of the hemispherical shell. Okay, so normally when it comes to 3D objects, we write the mass by considering its volume. That's the norm, right? When you see a 3D object, we normally consider the mass is proportional to the volume. But over here, it's a hollow cylinder. It's a hemispherical shell, which means it's completely empty inside. So in the event that you're working, even though you're working with 3D objects, and if they're hollow, okay, and if they are empty inside, the volume cannot be taken as a representation of mass. Because if there's no volume inside, how can volume represent mass? Okay, so in such situations, okay, you need to work with area. You need to work in this case specifically with surface area. Okay, so you have to consider mass as proportional to the area. Okay, so guys, that's what I've done here, mass as a proportion of area. And so I'm going to get now you can see here in the hemispherical shell. So I only have the shell part, right? There's nothing, there's no circular base here. There's no base, okay? This is empty inside. So there's only the shell, okay? So basically the surface area of the shell, so it's, you can see here, it's, if for a full sphere, the surface area is 4 pi r square, right? So it's half a sphere. Surface area is 2 pi r square. Okay, 2 pi r square, and the radius is 2a. So you can replace radius with 2a. So r square, that's 2a whole thing square. That's 4a square into 2. That's 8 pi a square. Okay. And the center of mass, guys, the center of mass I'm measuring from O. So when I'm measuring from O, now the thing is, again, there are some concepts that you can directly use. So you've known in your M3 book, you've done the center of mass of a hemispherical shell, right? The center of mass of a hemispherical shell was half, if the radius is r, the center of mass was at half r. So these are some results that you can directly use and that you need to remember. Okay. So the center of mass of a hemispherical shell is half r from the center of the hemisphere. Okay, so that's half r plus the, since you are measuring the center of mass from O, you have to add the Ka height. So Ka height plus the half r. Okay, so that gives you the center of mass distance from O, the center of mass of the hemispherical shell. Okay, so that's what I've done here. And then the r value is 2a. Okay, so half into 2a, that cancels. You've got a remaining, a plus Ka. Taking a out, I get a times 1 plus k. Okay, guys, so that's the center of mass of the hemisphere. So moving on to the cylinder. So cylinder again, when you're considering the mass, now remember in this case of the cylinder, there's no top lid, right? But I think you saw there is a bottom lid. There is a bottom lid, right? Because the bottom of the thing is closed. Okay. So there is a bottom lid. They say it here. Okay. When you read the question carefully, you have a lid at the bottom. So, but when I'm taking the cylinder, I'm not, I've taken the cylinder as a hollow one. So there is no bottom lid here. So this is both open and ends are open in this cylinder. Okay. So I've only taken the middle section. Okay. Only the middle section. No lids here. Okay. So then in that case, I need to consider the surface area or the curved surface area of the cylinder. So how do I get the curved surface area of the cylinder? So guys, you need to remember these formulas. Curved surface area of a cylinder is 2 pi r h. 2 pi r is the radius of the circle and h is the height. So when you multiply the radius of the circle into height, you kind of get the area of the rectangle, right? Because this is a rectangle that you bent to form the cylindrical body, right? So 2 pi r into h, and radius is 2a, height h is ka. You can simplify and get this. And the center of mass from O is, the cylinder center of mass is exactly in the middle. So it's half of Ka. And the bottom lid, so you can see I've now taken the bottom lid separately. So bottom lid, the center is at, it's directly on this point, right? So the mass is the area of the circle, pi r square. So radius is 2a, pi into 2a square. So that's this guy. And the center of mass distance from O is 0. So let's consider, put everything together now. So the total mass is when you add all of these areas. That's what I've done here. So I've added all of them. And I've taken here the common things out. Okay. And then the center of mass is y bar. Okay. And then we are going for moment equation, right? So what do? We multiply the mass and the center of mass. And you can see everything here is an addition because we don't remove any part. We add each part to complete the, to make the complete object. So 8 pi a square into a 1 plus k, 4 pi k a square into ka over 2 plus 4 pi a square into 0, okay, equals the final, equals total mass into center of mass 4 pi a square 3 plus k into y bar. Right, guys, can you see? So I've just used the values of the table. I've multiplied the mass and the center of mass. This is basically M2, right? Where you multiply the sigma of the mass and the coordinate, the distance. Okay, so here all of these parts were addition and this equal total mass into the y bar. So you can see this is basically simplification. I've cut off the pi a square from everyone. That's common. And here I've got 8k1 plus k remaining. Here I got so 4k and kk square a over 2. And this is a 0. And here 4, 3 plus k. So this is all simplification from this point onwards, right, guys? So you can figure this out, right? 8a, 8ak, this is 2ak square. And you can see here, I've taken this guy down. I've taken 2a in front, right? I've taken 4 from the denominator. I've simplified, and you know, it's a basic simplification. And it's okay. So this is the y bar. So there's a question: why is the center of mass for bottom lid 0? So the center of mass for the bottom lid is 0. Why? Because it's on O, right? Because you are measuring the vertical height from O. So from O, the vertical height, the lid is 0, right? This lid is not located above O. It's exactly on the same level as O, right? So that's why it's a 0. Okay. Then, so that's the 5-mark question. Moving on to the next one. The container is placed with its circular base on a plane which is inclined at 30 degrees to the horizontal. The plane is sufficiently rough to prevent C from slipping, from sliding. The container is on the point of toppling. Find the value of K. So guys, this is from chapter 6, right? Where you talk about sliding and toppling. So they say here that they take this container and they keep it on this inclined plane, right? So they keep it on the inclined plane and which is inclined 30 degrees to the horizontal. The plane is sufficiently rough to prevent C from sliding. The container is on the point of toppling. So you need to recall the requirement for toppling, right, guys? So what's the requirement for toppling? So if you recall, the requirement for toppling. So I think we've done the theory parts, right? So I'm just gonna quickly give you the overview because we've done this in the theory classes. So basically, the weight needs to go from the very last point of this contact surface, right? Okay, the weight. So this is the complete diagram, right? The weight needs to go from the complete because this is the toppling point. This over here is the toppling point. The weight goes from the very last toppling point. Then the center of the normal reaction is also acting at that very edge, and then you have the friction as well, right? So that's exactly what we have here, right? The weight acting at the very last point. The normal reaction should act from here, and the friction, the resistive force acting here. All three forces can meet at this single point. Okay, so this is where you have the point of toppling. Okay, when the weight goes through the very last point here. That's the geometry you need to consider here, right? So I've explained the reasoning behind this geometry. right? In the theory work. Okay. So we are going to directly use this and build up our equation. So so this is your center of mass, right? The weight starts from the center of mass, from G, right? So this is G, and from O to G is your Y bar, right, guys? Because Y bar is what we found in part A, and that was the vertical distance from O to the center of mass. So tan 30 is opposite over adjacent. So opposite is 2-way, adjacent is Y bar. So the y bar values we found here. So tan 2-way divide by, I just written here, divide by, you can write it downwards, that's up to you. Okay, this is just basically simplification. The most important thing here is to get this diagram and to write this expression. So that's it. If you can write this expression and write that tan 30 is opposite over adjacent, that's 2-way over y bar. That's it. Okay, so that's the most important thing here. And then you can input your y bar value, and then I've turned division to multiplication. So this is basically simplification from this point onwards, right? The a cancels, and you actually get an equation in terms of k. Okay, you actually get a quadratic equation in terms of k, right? So you can see I've multiplied here. So 3 times the 3 comes up, 2 times 2 is a 4. 4 with this 3 has become a 12 times k plus 3 over k square 4k plus 4. I've taken the k square 4k plus 4 the other side and multiplied with root 3, and it's equal to 12k plus 36. And then I've taken the 12k plus 36 to this side. I've factorized, right? Taken the k square terms separately, k terms separately, and the constant terms separately. And then you solve for the quadratic equation. So you solve for your quadratic equation, and then obviously k should be a positive figure because you can see it's ka is the height, right? So k can't be negative. Okay, so k has to be some kind of a positive figure. And you can get your k value and you can leave it correct to 3 significant figures. Okay, guys. So this is the working and the reasoning behind question number 4. Okay, guys. So we'll move on to question number 5 now. A particle P is moving along the x-axis. At time t seconds, the displacement of P from the origin O is x meters, where x equals 1 over 4, x equals 4 cos 1 over 5 pi t. Okay. So prove that P is moving with simple harmonic motion. Okay. So guys, we had the SHM question, right? So how do you prove an object is moving with SHM? The equation you need to derive is x double dot equal minus omega square x. So if any particle is moving with SHM, and if you can prove that the characteristic equation of the acceleration follows this particular format, then we immediately say you proved it's moving with simple harmonic motion. So all you need to do here is they've given you the x value. All you need to do is to get x double dot. What is x double dot? That is when you differentiate x twice, right? Differentiate x once, it's x dot, and that's the velocity. And if you differentiate x twice, x double dot, that's the acceleration. Okay, so this is pretty straightforward, guys. Okay, so it's just 3 marks, and the method is really easy. So you can see what I've done, right? So we take x equals 4 cos 1 over 5 pi t. We differentiate it once. Okay, so cos differentiation is minus sine standard differentiation, right? Sine of the angle into the inside differentiation of the angle 1 over 5 pi t differentiation is 1 over 5 pi. Okay, so this is P3 differentiation. So I've just rearranged the equation and written here again, right? So this is basically simplification, guys. Be careful, don't make mistakes. So it's minus 4 over 5 pi sine 1 over 5 pi t. Okay, so first time differentiation is done. Going for the second derivative. So in the second derivative, minus 4 over 5 pi is you leave it as it is, and sine differentiation is cos. Okay, sine differentiation is cos 1 over 5 pi t, and then standard rule into, you have to, chain rule, you multiply with the derivative inside, right? So 1 over 5 pi t derivative is 1 over 5 pi. So now simplifying, so minus is there 4 over the 5 into 5 is a 25, and the denominator pi into pi square, and you get cos 1 over 5 pi t. Okay, guys, so I get x double dot in this format, but that's not the format I want, right? Because I want to get it in this particular format. I need to show x double dot is minus omega square times x. There should be an x in here. Omega is a constant, right? I need to somehow input a x back into the question. So if you check, guys, you can see x is 4 cos 1 over 5 pi t, right? So you can see here that I'm doing a rearrangement to this question. So I'm having 4 over 25 pi square. I'm keeping the pi square over 25 and bringing the 4 here, right? It's just a multiplication. So you can switch positions. There's no problem, right? So then 4 cos 1 over 5 pi t is your x. Can you see? So I replaced the 4 cos 1 over 5 pi t as x over here. This guy is replaced by x. So it's minus pi square over 25 times x. And that's it, right? That means that this shows that I've proved that my object moves in simple harmonic motion, right? So this is the pi square over 25 is the omega square, and this is the x. So even at this point, it's enough. I've gone for one further step of simplification, but this is enough. And if you show it, that x double dot is equal to some negative constant times x, then that's it. And you proved that your particle moves in simple harmonic motion. Okay, so that's the answer for part A. We'll move on to part B. They ask you to find the period of the motion. So how do you find the period of the motion? So that's based a standard equation, right? In oscillation, the period of the motion is 2 pi over omega, right, guys? So these are things you need to know already, right? So these were covered in the theory classes. You're directly supposed to use it. It's just 2 marks, right? 2 pi over omega. So 2 pi and omega, you've identified from part A. Because in part A, you got the omega square is pi square over 25, so which means omega is pi over 5. Can you see? And you replace that, and you can get here the period of the motion as 10 seconds. Okay. And then part C state the amplitude of the motion, and you can see it's just 1 mark, and it's state, not derive, not find, right? So it's just a state. So when you just state, guys, you need to see now. That's what I have written here. Now, when you look at this particular format, guys, you need to see that it is of the format x equals a cos omega t. Right, guys? Because if you recall in SHM, you had equations of the form x equals a sine omega t, x equals a cos omega t, right? So this is a form x equals a cos omega t, right? So this is where the equation you use when your particle starts the SHM motion from the amplitude instead of starting at the center. You use x equal a sine omega t when your particle starts the SHM motion from the center of the SHM, right? So anyway, this is of the form x equal a cos omega t, and immediately your a is actually 4, right? You just have to state it because you can even see the omega value is actually here, right? The 1 over 5 pi, okay? Because if it is of the form a cos omega t, so ignoring the t, the 1 over 5 pi is the omega, which we already got. Okay, but anyway, you can't just write that down here. You need to do part A. The derivation should be done, okay? The derivation, this work needs to be seen. Okay, so the amplitude is just a state. So directly give it as 4. If you want to use any equation, you can, but it's not necessary. Okay, because it's just a state and 1 mark. Then part B, find in terms of pi the maximum speed of P. So guys, where do you achieve the maximum speed? You know, in SHM, you achieve the maximum speed at the center of SHM, right? Because at the amplitudes, okay, so this is the center of your SHM at the let's say this center. At the two amplitudes, the velocity is 0, right? But at the center, you have Vmax. You achieve the maximum velocity at the center of your SHM. So what do you do to find the maximum speed, guys? You know, you measure your x from the origin. I mean, you measure x from the center of SHM, right? So when you're at the center, the x value is 0, right? Do you recall this theory? When the particle is at the center, because you measure x distances starting from the center of your SHM. Right, so we use v square equal omega square a square minus x square. This is a standard equation. And I want to find the maximum speed. I know I want to find v. I know omega and I know amplitude. And I just need to input the x value. So we know to achieve the maximum speed, x has to be 0. So we replace x with 0 and we simplify, right? So we replace the omega with pi. Omega square is pi square over 25. Amplitude is 4, so that's 4 square because it's a square. And then you simplify, right, guys? And you simplify and you take finally the square root. And that gives you the v value. Okay, so this I can directly leave the answer because we can see it in terms of pi if you input the value of pi. So they say here in terms of pi. Okay, so that means you give an exact answer. Okay, guys. Okay, so I'll move on to the next part. They say the last part, right? 4 marks. Okay. The points A and B lie on the x-axis on opposite sides of O. Okay. So opposite sides of O means O is actually the center of oscillation, right? Okay. So O is kind of like the center of your oscillation. The origin O, yeah. This is actually this should be O because your displacement is happening around O. The center of mass is happening. Sorry, the simple harmonic motion is happening about O, right? Okay, the points A and B lie on the x-axis on opposite sides of O with OA 1.5 meter, OB 2.5 meter. Find the time taken by P to move directly from A to B. Okay, guys, you need to find the time taken by the particle to directly move from A to B. So, in order to do this, guys, I mean, I can, so this is the way that the approach that I've taken. So you can take different approaches, okay? So what I've done here is directly the time taken from A to B. Okay. So if I want to find the time taken from A to B, I'm going to break this into two sections. I'm going to first find the time taken from A to O, and then I'll find the time taken from O to B. Okay. So I'll first find the time taken from A to O, and then I'll find the time taken from O to B. So I'm going to break this into two. Okay. And then to find the time taken to move from A to O, guys, I know that the simple harmonic motion, when it comes to this motion, it's kind of symmetric, which means the time taken to move from A to O is exactly the same time as it takes to move from O to A. The time taken here, if it is T1, here also it's T1. It doesn't change. I mean, from the time taken on its motion, now, if you are considering from amplitude here, when the particle moves like in this direction, the time it takes to go from A to O, and while it's on the other direction, the time it takes to go from O to A is exactly the same. Okay. So I'm going to use the fact, I'm going to use that fact and find the time t1 because if the particle starts its oscillation from the center, we can directly use a sine omega t. Right, guys? Do you recall? You use x equal a sine omega t when the particle starts movements from the origin. So if I consider O to A, then I can think the particle started at the origin, right? So then if it starts at the origin, we can use x equal a sine omega t. Okay, so x is the distance, O to A, that's 1.5. Amplitude is 4. Okay, that's a constant. Sine omega is pi over 5 T1. Okay, so T1 is the time taken from O to A or A to O. Okay, guys, so you can see it's a matter of simplification here. So that's the first equation. And similarly, you can do a similar approach to find the time taken from O to B. So O is the center, to B is again x equal a sine omega t because particle starts motion from the center. So amplitude is 4 and omega value is 5 over 5. And here the time taken, I've taken it as T2. Okay, and then it's a matter of again simplifying, right? So taking the other side, OB distance is 2.5, taking 4 down, taking sine inverse of this guy, and then taking the pi over 5. So this is just simplification. 5 over pi, sine inverse 5 over 8 is T2. Similarly, over here, when you simplify, so guys, this is simplification. I think you guys should be you should be able to handle the simplification, right? So you get 5 over pi, sine inverse 3 over 8 is T1. And then you need the time taken to go from A to B. So you add these two values, right? So you add the time 1 and time 2. And guys, you can make sure your calculator is in radian mode. Okay, when you type this stuff, the calculator must be in radian mode. Make sure it's in radian mode, and then you get your answer and you can make it to yourself. Okay, guys. Okay, guys, we'll move on to the next part, next question. So question number 6, a particle P of mass 1.2 kilogram is attached to the midpoint of a light elastic string of natural length 0.5 meter and modulus of elasticity lambda newtons. The fixed points A and B are 0.8 meters apart on a horizontal ceiling. Okay. So can you see I've drawn it here. The fixed points A and B are 0.8 meters apart on a horizontal ceiling. One end of the string is attached to A and the other end of the string is attached to B. Initially, P is held at rest at the midpoint. Okay, midpoint M. So P is your particle with mass 1.2 kilogram. It's held at the midpoint of the line AB, and the tension in the string is 30 Newton. Okay, show that lambda equals to 50. Okay, so how do we do this one? Okay. Initially, P is held at rest at the midpoint, okay, of the line AB, and the tension in the string is 30 Newton. Show that lambda is 50. Okay, guys. So how do we get about showing this? They just want you to show the lambda value, right? They've given you the 30 Newton. They've given you the tension of the string, so you really don't need to do anything much here, right? And it's you just need to show that lambda is 50. So showing lambda is 50 here, guys, it doesn't require, because I think you can see, I think in this question, it's best to read the rest of it also, because they say, because over here, they said the particle is now held at rest at the point C, which is 0.3 meter vertically below A. So that is a different story, right? So which means when you're doing part A, you need to consider this particular kind of situation, right? So, so just read through this a little bit before you start. Okay. So here, in order to show that lambda is 50, okay, in order to show that lambda is 50, they don't ask you to do anything much. All they want you to do here is you can use the T equal lambda x over L equation, the tension for elastic strings, right? So this is the equation, the tension equation for elastic string. Tension is provided to you. So you can immediately input the tension value as 30. Lambda is the constant, the elasticity constant, and then the x value. So x is, guys, the x is the extension, right? The extension, the length that the string is stretched beyond its natural length. So here the elastic string has natural length 0.5. Okay, but the full extension is 0.8. Okay, so full extension is 0.8, which means from 0.5 to 0.8, the extension is 0.3, right, guys? So the extension is 0.3, and then you divide by the natural length, which is 0.5. Okay, guys, and that gives you the lambda values. This is just considering the string and nothing to do with the mass. Okay, so it's just considering the dynamics of the string. You have a string with length, natural length 0.5. And basically you're stretching that string to a length of 0.8. So then what's the lambda value? Because when you stretch it to a length of 0.8, the tension is given to you. Okay, guys, so you don't have to do anything much and nothing to concerning with the M here. Okay. Uh, okay, nothing concerning with the M. Just to consider the dynamics of the string should give you what you require. Okay. And then I'll move on to part B. Okay, so this is where the particle M is coming into the sum. Okay, they say the particle is now held at rest at the point C, which where C is 0.3 meters vertically below M. The particle is released from rest. Find the magnitude of the initial acceleration of P. Okay, how do you find the initial acceleration, guys? Okay, so the particle is now held at rest at the point C. So you can see I've drawn it here, which is 0.3 meters vertically below M. This is the point C. Okay, it's 0.3 meters vertically below M. And you know, M is the midpoint of the string, right? So we are pulling it vertically 0.3 meters down. Okay, so find the magnitude of the initial acceleration. Okay, guys. So what do you do? So when you're pulling this particle down and you're releasing, so what's happening? So we anticipate the particle to move to start trying to move up, right? Because you are pulling it down to a distance of 0.3, and then it's trying to move up, right? It's an upward direction. So that's what they're asking you to find the initial acceleration. Okay, so in order to find the initial acceleration, guys, I've considered here again. I'm gonna apply F equal ma. Okay, so I'm gonna apply F equal ma in the upward direction. But before I do that, guys, I need to find a few different things now. The first thing is the tension, because you can't say the tensions are exactly the same now, right? Because when you pull this distance of 0.3 meter down, guys, you can see now the length of the string is changing, right? Because it's not 0.8 anymore, right? So this was the initial position. You pull this down. So now you have a new length of the string. So you can see I've got the new length of the string by the 0.5. How did I get the value of 0.5? So this I got by using Pythagoras theorem. So you can see here this is 0.4, this is 0.3. So then this should be by Pythagoras theorem 0.5. Okay, because it's a right angle triangle. And if this end is 0.5 meters, the other side also should be 0.5 meters, right? Which means the total length of the string is 1 meter now. Okay, so now the total length of the string is 1 meter, and you can use tension equal lambda x over L. And so you know your lambda value. The lambda value we found as 50. Okay, and for this x over L, lambda is 50. The x is the extension beyond the natural length. So natural length 0.5. So extension, if this is 1 meter, you can use the extension as 0.5. Yeah, over natural length is 0.5 meters. Do you see, guys, what I've done? Okay, so the extension, because the whole string is 1 meter, 0.5 is 1 meter, and the natural length is 0.5. So the extension is also 0.5. Okay, and that gives you the tension in the string. The tension in the string is 50 Newton. Right, guys, are you with me? And then using the tension value now, because you know the tension that's acting on the string, you can now use F equal ma to find the initial acceleration. Okay, because you're supposed to find the initial acceleration. So we can use F equal ma upwards. And what are the forces acting upwards? So you can see I marked equal angles here. Once again, why do I mark equal angles? Because this is from the midpoint you're pulling down, right? So the length of the strings on either sides are equal and the angles are equal, right? So these are basically two equiangular triangles. That's the same in every aspect. So you can see I'm gonna take the forces acting upwards. So the forces acting upwards are 2t cos theta, right? Why have I used 2t cos theta? Because there's a t cos theta from this end. Okay, when I resolve this t over here, the first t I get upwards the t cos theta, and the other t on the other side. There's another t here, right? This t. So this one also resolves and gives another t cos theta. So altogether a t cos theta and another t cos theta gives you 2t cos theta. Minus 1.2 g is the weight acting downwards equals mass into acceleration. Mass is 1.2. And then 2 times tension is 50 we found. And cos theta, guys, you can find it, right? Cos theta can easily be found. It's because you are, I mean, you know all the three lengths. Cos is adjacent over hypotenuse. 0.3 over hypotenuse is 0.5. Like basic O-level trigonometry, right? Cos theta is adjacent over hypotenuse. 0.3 over 0.5 is what gives you 3 over 5 here. Minus 1.2 g equals mass into acceleration. 1.2 is the mass. Acceleration is what you're trying to find. Okay, so remember I'm finding the acceleration at this very specific point here. Okay. And then, yeah, so you can finally simplify and give your answer 3 years. So I've used G as 9.8 and I'm giving my answers to 3 significant figures. Okay, guys. So here, so this is my approach of doing this particular sum. Okay. Okay, so moving on to part C. Find the speed of P at the instant immediately before it hits the ceiling. So basically you are pulling. Now you know what's happening here, right? You've taken the particle C 0.3 meters below the ceiling, and then you're releasing and it's gonna go and hit the ceiling, right? So it's gonna move up and it's gonna hit the ceiling, and they ask you find the speed of P at the instant immediately before it hits the ceiling. So just before, just as it arrives to the ceiling. Okay, so guys, in order to do a sum like this, okay, now we know here the acceleration is not constant, right? Definitely the acceleration is not constant, because you can see it depends. The acceleration is actually going to be a function of uh, kind of like displacement, because you can see as the string moves up, you can see that the extension, the tension is going to change, right? Because the tension is depending on the extension of the string, and the extension of the string is going to change at every position while the particle is moving up, because when the particle is moving up, the string gets shorter in length, right? When the string gets shorter in length, I hope you guys can see, because when the particle is on its moving up like this, so these are the positions of the particle. So the string length becomes shorter, the tension is the value is changing, the extension value becomes smaller, and then so basically the acceleration is not constant. That's what I want to emphasize here. Okay, the acceleration is not something that you can keep constant here. Okay, so in these kinds of situations, it's best to find the speed. If they ask you to find the speed, now you can't work with this acceleration to any other point other than the initial point. Okay, so there's no point of working with this acceleration, and you cannot treat it as a constant. Okay, that's very important. So what you need to do here is, guys, in a situation like this with changing acceleration, the best solution to find a speed the best, or in other words, the only way that you have, the only way you can find a speed is by considering work energy principle. Or in this case, actually energy is conserved, right? Because you don't have any resistive force, you don't have friction or any other type of thing. There are no non-gravitational resistive forces here. So which means energy must be conserved. Okay, so by using the conservation of energy principle, you can easily find the speed. Okay, guys, so all you need to do here is consider all the energies at the point C and at the point M. So because, energy should be conserved. Whatever the energy you have at C is what you have at M. Okay, so converted. So what are the energies we have at C? So at C, you can see I've considered C as my GP zero level, right? So I've considered this as the lowest level as the zero level, which means there's no height here. Okay. And at this point, what do we know? We know we release from the particle is released from C at rest. The particle is now held at rest at the point C. So which means you're releasing it from rest. So at point C, guys, you don't have there's no kinetic energy because you're releasing it from rest. And there's no potential energy because I marked GP zero level here. It's the lowest level. So what energy do I have at C? The only energy I have at C is the elastic potential energy, because you have the string is stretched and the string provides the elastic potential energy. So you can find the elastic potential energy at C by using lambda x square over 2L, right? You know this equation, you've learned it in chapter 2. This is the elastic potential energy of a string, and the extension at this point C is 0.5. Just substitute the value. Lambda value is known, extension at C is known, 2 times natural length is 0.5. You can substitute all the values and get the elastic potential energy at C. That's the 12.5 here. Okay, so this is equal to, what are the other energies? So these are the energies you have at M. Okay, because energy is conserved. So at a point M, the particle comes and hits the ceiling, which means it has a kinetic energy, right? There's some sort of amount of kinetic energy. And also at M, you are above the lowest level, which means you have some sort of potential energy. And also, guys, even though you are at M, the string is still stretched, right? Even though you are at M, that this is still a stretched string. There is elastic potential energy on this point as well. Okay, so there's elastic potential energy on M as well, right? So what I'm doing here is conservation of energy, considering energy at the lowest point and comparing it to the energy at the highest point, and they must be equal. So you can see I've done the elastic potential energy at M. I've just worked it out separately here. So lambda x square over 2L is the equation. Lambda is 50. That's the elasticity constant. And extension, guys, at M, I think we saw in the very first part also, the extension was 0.3 because the total length of the string is 0.8. Natural length is 0.5. So 0.8 minus 0.5 gives you the extension 0.3, and 2 times natural length 0.5 gives me the elastic potential energy at M, which is 4.5. Okay, guys. So all I have to do is to substitute the values into this equation, right? Elastic potential energy at P is found. That's the only energy you have at P. At the very top point, you have kinetic energy, half mv square, potential energy mgh, and elastic potential energy we found as 4.5. So guys, it's a matter of substituting all the values into the equation, right? So half the mass is given as 1.2 kilogram. V is what we are trying to find. V is what we are trying to find here, right? Plus mgh, mass is known, G is 9.8, height is 0.3, plus elastic potential energy 4.5. So guys, you put everything together and then we make V the subject. This is just a matter of simplification. Definitely give your answers to 3SF or 2SF because you've used G as 9.8 in your simplification. Okay, do not leave exact, do not leave extra decimals. Just 3SF or 2SF is sufficient. Okay, so this is simplification, and I think this part should be clear with you guys, right? So this is just simplification and finally making you the subject. Okay, guys. Okay, guys, moving on to the last question. A particle P of mass M is attached to one end of a light rod. Okay, so it's a rod of length L. The other end of the rod is attached to a fixed point O. Okay, so I've kind of done, let me, okay, so you can see the figure now, right? Okay. Okay. They say here particle P of mass m is attached to one end of a light rod of length L. Okay, so this is the rod, the length is L. The other end of the rod is attached to fixed point O. The rod can rotate freely in a vertical plane about O. The particle is projected with speed u from a point A. So guys, can you see this is the point A and you are projecting the particle with speed u from point A. The line OA makes an angle alpha with the upward vertical through O where alpha is smaller than pi over 2. So that means it's an acute angle. Okay. So when OP makes an angle theta with the upward vertical, so it's all marked on the figure here, guys. Okay. So when OP makes an angle theta with the upward vertical through O, the speed of P is V. Okay. The speed of P is V. That's also marked. As shown in figure 4, show that V square equal U square minus 2GL cos theta minus cos alpha. So guys, you immediately know when you take a look at this equation what we are dealing with here, right? So you need to realize what you are working with. We are working with a circular motion, basically a vertical circles, right? So this is the vertical circular motion sum. Okay, so when you're working with these kinds of sums, I think in theory you've done in textbook you might have derived equations quite similar to this format, right? So what's the basis here? In vertical circular motion, the basis we use is we use conservation of energy, right? We use the law of conservation of energy, and we use F equal ma towards the center. So those are the main methods that we use. So you can see here what I've done. I've used the law of conservation of energy. Okay, so guys, I've marked here at this point now. When I use the law of conservation of energy, you need to mark what's your, because you're measuring your height. You need to kind of set a zero level. So I've set the origin as a zero level. You can set it as you wish. Okay, if you want the lowest level, then you can do that. But it will not change the dynamics of the sound. Okay, just that the heights are going to change and it will change on both the sides and things won't be affected. Okay, so what do I do here? So you can see here, I've marked the zero level. Okay, so this is considering the movement from here to here, right, guys? So what do I have? What energies do we have? So in the beginning, I have kinetic energy and plus I've taken the potential energy, right, guys? So how have I taken the potential energy? Now you can see here mgh I've written as mg L cos alpha. How have I taken this L cos alpha, the height? So I'm measuring the height with respect to the GP zero level. So this is my GP zero level, right, guys? So you can see I'm trying to find this height because I want to find the vertical height from the point A to this horizontal level. So guys, I know the radius of the thing is L and I know this angle alpha. Can you see? I can take it as, can you see here? This is kind of like a alternate angle. Can you see this angle alpha here comes over here through alternate angle? Okay. So that's how alpha comes here. Okay. Alpha is this large angle. Alpha is this large angle, right? So alpha comes here through alternate angle. And then you can resolve the hypotenuse L cos alpha is the height. Can you see L cos alpha is the vertical height? So very important. So that's how I've got the L cos alpha, right? So the the energy at point A is kinetic energy plus potential. Kinetic energy is half mu square because the speed is u. Plus the potential energy is mgh and the vertical height is L cos alpha. Okay, that's the energy at A. So you equate it to the energy at P at this point. So how do we get the energy at P? At point P, the speed is v, so that's why it's half mv square. And again, you have to get the vertical height. MGH, you have to get the vertical height to the GP zero level. So how do I get the height to the GP zero level? So guys, again, you can see I've considered alternate angles now, this way. Can you see? And this angle is theta. And that theta angle comes here, right? Through alternate angle. So, and then I know again the radius is L. So this radius is again L, right? This distance is again an L. So it's gonna be the height. This is the vertical height, right? Of the particle, the GP is 0 level. So this height is gonna be L cos theta. Can you guys see? It's L cos theta. So that's how it's done. Okay, so I hope that part was clear. Okay, the vertical height I've written it here. It's L cos theta. So all you need to do is to apply that into your equation. So mgh is mg, h is L cos theta. Okay, guys. So that's the energy, comparing energy at A and P. So now it's time to simplify. The m simplifies out, and half u square plus gl cos alpha, half v square gl cos theta. I multiply the whole thing by 2 to get rid of the half. I get u square plus 2gl cos alpha plus v equal v square plus 2gl cos theta. And then, guys, you can see it's just a matter of rearranging the equation to get the show that. So I can rearrange this equation and get v square. Right? Is that clear? I think there should be, there's nothing difficult here, just to apply the law of conservation of energy and rearranging the equation to make v square the subject. Okay. All right. And then let's move on to part B. So in part B, they say, uh, given that cos alpha is 2 over 5 and that u equals root 3 GL, show that P moves in a complete vertical circle. So how do you show that the particle moves in a complete vertical circle, guys? So you know when it comes to vertical circular motion, the most challenging point that the particle needs to pass through is the very top, because if it manages to pass through the top, it will definitely complete the rest of the thing. Okay, so the place to pass is the very top, the topmost point. So if it can pass through the topmost point, then it's managing to go through the entire vertical circle. But how do you show it manages to pass to the topmost point? So there are different requirements for rods and for strings, right? So you need it's clearly explained in the we did in the theory work, and in your textbook you can see for rods, for strings, the requirements to pass through the top of the circle are different. Okay, so for a rod, the requirement is that the velocity at the top should be greater than or equal 0. So that was the requirement. Okay, so that's what I'm gonna do. Okay, so let's see. Okay, so I want to show that at the very top point there is some kind of a positive velocity. Okay, so let me remove this. Okay, so I want to show that the velocity at the very top is there is some kind of value. It's not 0. Okay, I want to show that it reaches the top, and it reaches the top with some kind of a positive value. So if there is a velocity over here, that means it reaches the top. So how do we do that, guys? So you can see here, my attempt is to find the velocity at the very top point, so at the topmost point. And you can see I have already derived a general equation for the velocity, right? Because you can see I have an equation for the velocity in terms of theta. Okay, remember theta is our variable, alpha is not the variable. Okay, how do I say that theta is the variable and alpha is not? Because alpha is the place where you started, right? A is the position where you started. Okay, guys, and so this u was a fixed velocity because this is the starting velocity, and that's not a variable. The variable here is v, because you can see here the particle is going through this path, and this p is a general point. The p we used here, this point p that you used here is a general point. Okay, so a general point can be anywhere. Okay, and that is measured in terms of theta, and this theta is a variable. Okay, so remember A is the place where you started, starting point. Starting point is not a variable. That's something that they gave you, and that is not something that you can change as you want. So you can't change the starting point to anywhere you want and give u again. No, starting point is a fixed point that they give you. So then this alpha and this u, these are fixed values. These are constant. You can't do anything about it. But P is a general point, and you can see that you can change this theta value and get the V value as you wish. Okay, so at the very top point, what happens, guys? So when P goes to the very top, you can see this theta angle reduces to 0, because theta is measured from the vertical, right? Can you see? The angle theta is measured from the upward vertical. So when P goes to the very top, your theta angle reaches to 0, because you reach this point and the theta is measured from the vertical. So if you add the vertical, theta is 0. Okay, so that's what you need to do here. So you have the general equation for the velocity, this equation, okay? And you set your theta to 0. You set your theta to 0. And guys, you input the value. Okay, I think the cos alpha value is given to you, right? Yeah, see, cos alpha is a fixed value, 2 over 5. That's given to you. And u is root 3 GL, again given to you. As I told you, they are fixed, right? They're fixed. So you input those values, and you can actually prove. See, you can show that your v value is a positive figure bigger than 0. So if at the topmost point, okay, so if at the topmost point you have a positive velocity, it means the particle is definitely moving in a complete vertical circle. Okay, guys, so that's the most important thing. Okay, showing that the topmost point velocity is greater than 0. Okay, so this is simplification. Okay, so you guys can come to this conclusion. Okay, so I'll move on to the last part. As the rod rotates, the least tension in the rod is T and the greatest tension is KT. Find the exact value of T. Guys, you can see it's 9 marks. Okay, this is where most of the marks lie in this question. Okay, so now the question I need to ask from you. Okay, you need to know this before starting. So where do we get the least tension and where do we get the greatest tension? There are very specific points. Guys, so there are very specific points in a vertical circle where you have the least tension and where you have the greatest tension. So guys, you should know that. So where do we have the least tension and where do we have the greatest? Okay. So remember to get the least tension and the lowest tension, guys, it's at the one is at the topmost point, the other one is at the lowest point. Okay, so okay, let me explain to you how this works. Uh, okay, so guys, how do we assign? The first thing is you should know the lowest and the highest tensions are coming at the directly the vertical point. Okay, so how do we assign which one is the lowest and which one is the highest? So guys, you should know this stuff when you cover the theory in the M3, right? Because you should know that all the other point at considering all the other places, these are the two places where the all the forces are acting completely vertical, right? So you're having a rod, and if it's a rod, the tension is acting. So over here, the tension is acting downward, and over here, the weight is also acting downward. Can you see? But on the other side, if you're on the other end of the circle, the particle is here, you can see the tension is acting up and the weight is acting down. Okay, so this is so this doesn't happen in any other place. In all the other places, your tension and mass is not acting on the same line, right? So then you'll have to resolve, and when you resolve, those tension values are smaller. Okay, these are so these are the two special points where you have the lowest and highest. And now, who is the lowest and who is the highest, guys? So here you can see at the topmost point, the tension and mg are both working together. Okay, at the topmost point, the tension and mg are both working together. So you can see, you need to realize here, guys, okay, because the tension and mg are both working together. This is the place where you have the lowest tension. Right, this is the place where you have the lowest tension, and this is the place where you have the highest tension, because over here the tension is taking the entire weight on its own. Here tension and weight are sharing the load of the circular motion, right? But here the tension is taking the entire thing like on its own. Okay guys, so I think if you go through the sums that you've done in your circular motion lesson, you should be able to see there were certain questions that we did where this was emphasized, right? So I think you can go through those stuff as well. So and you need to see it though here, right? Because tension and mg are working with each other, so which means they the tension value and mg are working together, but here the tension is and mg are separately working. Okay, and then which means the tension is on its own. Okay, so the tension is going to be higher here. At the lowest point, tension is higher. Okay, so then I'm going to we're supposed to find the lowest and the highest grade. Okay, so they've given us the least tension in the rod is T and the greatest tension is KT. Find the value of K. Okay, so they've told us the least tension is T, greatest tension is KT. So greatest tension is KT. I have to put KT here, right? This is KT and this is just T. Okay, so guys, let's apply the other rule. So I applied law of conservation of energy. The only rule remaining for me to apply is F equal ma towards the center. So we apply F equal ma towards the center. Tension plus mg equals ma. In this case, I'm not going to use r omega square. You can see I'm using for centripetal acceleration v square over r. Why am I using v square over r? Because I have the equations with I know the v value because I have an equation with v square. Okay. And guys, at the topmost point, the V value was found, right? At the topmost point, we found that the V value is root 9GL over 5. This was found in part B at the topmost point. So you can replace the V value with 9GL over 5 and you can get the T value. Okay, guys, can you see the simplification? You can do it. Okay. And then at the lowest point, guys, you have the highest tension. Okay, at the lowest point, we have the highest tension. But the thing is, at the lowest point, in order to find the tension, guys, I need the speed because again, I'll be using this equation. Okay, the dynamics will change slightly, but I need the speed at the bottom in order to use F equal m. So the first thing is to find the speed. So you can see what I've done here, right? And so I found at the lowest point, I'm finding the speed by using this equation we derived in part A. And at the lowest point, what's the theta value, guys? So at the lowest point, you can see the theta value is going to be 180, right? Even the other side because theta is measured from the upward vertical. So if you're at the other side, if you're at the bottom, the theta angle is going to be 180. Okay. So you can mark the theta angle as 180. Okay. In here for the theta, cos alpha and everything else is given to you. U value is given as 3GL. It's given in the question. U square and cos alpha values were given. So substitute those values. Okay, those are constants, as I told you. That doesn't change, cos alpha and u. Okay, and you can find input the theta as 180. If you do this, the calculator should be in degree mode. If you use pi radian, you can use the calculator in radian mode. And you can get the value, the speed at the very bottom. This is the speed at the lowest point. The speed at the lowest point, and then we apply F equal ma at the lowest point. So at the lowest point, when you apply F equal ma, the force towards the center is the kT, the tension. Okay, the tension here is the maximum tension, which is, I think I'm replacing kT at the end. So this is the maximum tension. Okay, minus the, you can see I'm subtracting the tension, subtracting the weight. Tension is acting upwards, weight is acting vertically downwards. Nothing to resolve here because everyone is directly acting on the line towards the center. So T max minus mg equals ma, acceleration v square over r, and for v square, you substitute the lowest point speed. Okay, so v square is the lowest point speed. Here L is the radius, okay? This r is the L here. Okay, that's the radius. Okay, guys, so that's simplification. So you cancel things out and you take mg here and you can get the maximum tension, which is kT. The maximum thing is kT. And guys, K times T, we know the T value. The least value is T, right? The lowest tension was T, and that was 4 over 5 mg, which we found here. This is the lowest tension. Okay. I think I'm using L, it might confuse. The lowest tension is T. Okay. And then you guys just input the values here, right? So KT, just substitute. So KT is equal to 3 over 5 mg. And then you replace the T value with 4 over 5 mg because T is the lowest tension, the least tension. The least tension is 4 over 5 mg, and you can get your K values, guys. Right? I hope it was, I hope it was clear to you what I did. Right? So I got the lowest tension that is at the top of the circle. And I got the maximum tension at the, so let me use min max. This is the tension minimum. Okay, so this is the tension maximum is kT. So tension minimum. Okay, so tension minimum is the 4 over 5 mg. And this is what they say as T, because they use the word here, right? They say the least tension in the rod is T, which means the T minimum is the T and the maximum tension is kT. Okay, so I got the T minimum value. That's 4 over 5 mg. I got the T maximum value, that is the 34 over 5 mg, and that is equal to kT. So that means I can replace the T minimum value here because T is the T minimum. So T maximum equals K times capital T is T minimum. Can you see this T is the T minimum value? So that's what I did here. KT equals to T maximum and the T value is the minimum. Okay, guys? Okay, so I hope this is clear. All right, so yeah, so that's the end of our paper, right? Okay, yeah, so we are, yes, guys. So this is the end of the Jan 2022 M3 paper.